like to get a sense of how much do you guys know about paging. So for example, from the feedback that I received from you last week, there were at least like 3 or 4 people who explicitly mentioned that we learned about paging a lot more in detail in 354. And so the last part of the class where we discussed paging was like kind of redundant. And so it would be great if some of you can share like the level of detail that you learned with paging, because usually in 354 at UW we usually we just give a high level introduction to paging, but we don't go into like a lot more details. Yeah.
So yeah, when we took the before last semester, we went into all the page tables and we did a substantial amount of paging. That being said, it's super complex, so I was not one of the people that said that was redundant.
Got you. Okay. Any other thoughts or comments? Yeah.
Those of us who didn't take it last semester don't know anything. So.
Okay. So how many of you took, like whoever is here, how many of you took 354 with Ramsey last semester? Okay. At least more than half of you. Okay. Good. So okay.
I was looking at my notes from last semester during last lecture, and it wasn't as detailed as what you were going into.
Got you.
Because I only had like 2 paragraphs on everything that we covered in class.
Okay. Okay, then I think I'm just going to stick with my plan of like how we have been like doing till now. So maybe if you already know about, let's say, multi-level page tables, or why are we using TLBs and stuff like that in a lot more detail. Maybe I've got like a few worksheets for you just to figure out. So for example, these were like some worksheets from last, like from the summer. If you can, let's take an example, okay? So if you can figure out something like this is like a problem with a 2-level page table. I'm just like showing this just to like make sure that I'm not wasting your time. So if you can figure out something like this, we have like a 2-level page table, and there are like page directory entries, page table entries and stuff like that. And then the problem is to like, let's say given a virtual address, there are 2 virtual addresses. Can you figure out in this setup, can you figure out what is the physical address, or can you say if it will seg fault? And if you can figure out a valid physical address, then can you figure out the data value that is inside that particular memory location, given a physical memory dump like this. This is like a physical memory dump where we have like the addresses, like page numbers here. These are the physical frames, and then these are like the contents of the physical memory. So the goal of today's class would be like maybe at the end of the class, you would be able to like do something like this. Okay, so I'm just trying to let you know, like if you guys already feel like you can solve some problem like this, maybe you may feel free to skip today's lecture. Okay, but we'll also learn some things that other than this, but I'm just like trying to let you know, like I didn't want to like waste your time. Okay, so this is what we're going to learn today. Let's see. So worksheet, is this worksheet? Worksheet 3 is graded, but I just like forgot to bring it in for today's lecture. Sorry about it. I can give it to Zoen maybe tomorrow or on Friday. And Zoen has office hours on Thursday and Friday this week, since he cancelled his office hours like on Tuesday. And I can give it to him. You can collect it from him if you want, or again I can bring it like the next week to class along with worksheet 4. Any other questions on worksheet? Okay. So in today's class, okay, 5. So the main ideas that we're going to discuss in today's class is like we're going to review paging quickly. And then the important thing here is like we are going to discuss the issues with paging. There are two issues with paging with respect to the speed and with respect to space. Okay, and in the two solutions that we are going to see, we are just going to see like how are we going to tackle the speed, how can we make paging faster, and second issue is like how can we tackle the problem of space. By that we mean how can we make page tables to be of lesser size basically. So we can write it down later, but these are three things for today's class. So let's start with the review of paging. So again, for simplicity, again it's like a quick review of paging because like we want to like build on top of this. We want to see like what may be the problems with this, and then so that we can build on top of this for understanding today's class. Let's assume a virtual address space. Okay, let's assume a virtual address space of 64 bytes. It's maybe slightly different from the examples that we saw last time. So, and let's assume a page size of 16 bytes. So if this is given, then the first thing that I would usually think about is like if the virtual address space, entire virtual address space size is given, how many bits are there? So this is nothing but 2 to the power of 6 bytes. If you want to address 2 to the power of 6 bytes, you need like at least 6 bits. First we would like to draw those 6 bits here. After drawing these 6 bits, we should figure out like which parts of these bits form the virtual page number and which parts of these 6 bits form the offset. And for that, I would like to see like what is the page size. It is 16 bytes, which is nothing but 2 to the power of 4 bytes. And so we need 4 bits to uniquely identify each and every byte within a single page. Okay, and so we need, in this case, we need 4 bits. So for the offset, using the page size, you can figure out the offset, and then the remaining two, how many ever bits are there, are going to form the virtual page number. Okay, with this, now we can easily have like a diagram of our virtual address space. It's going to have, since we have only 2 bits for our VPN, we are only going to have like 4 virtual pages with VPNs 0, 1, 2, and 3. And each virtual page in turn is going to have 16 bytes in it. So this virtual page 0 is going to have like bytes 0, 1, 2 up till 15. So bytes 0 to 15 will be there in the virtual page 0, and bytes 48 to 63, the last 16 bytes will be in virtual page 3. With this setup, if we assume a physical memory, we can assume a physical memory, let's say of size double the size of the virtual address space, let's say 128 bytes. If this is our setup, physical memory, the total size of the physical memory, then the important thing to know is like whenever we have a page size, both the virtual address space and the physical address space or the physical memory is going to be split in the same size of the page size. So page size is going to be fixed for both the virtual address space and the physical address space. So since we already have fixed the page size, or we are assuming the page size to be what is happening. Okay. So if I assume since we are assuming the page size to be 16 bytes, we are going to have like 8 virtual pages here in the physical memory. see if it works this time. If it's not working, just let me know. If I'm not seeing that. Okay. So we can divide this physical memory into like 128 bytes into, if you're dividing it by 16, we get like 8 physical pages. And these are called the physical frame numbers. This is the physical frame number 0, physical frame number 1, 2, 3, 4, 5, 6, and 7. Okay. And then now, the high-level idea of paging is, since we have equal-sized slots in both the virtual address space and the physical address space, now you can just take one slot or like one page from this virtual address space and then fit anywhere in this physical address space, except some regions that are reserved. So for example, page 0 will be reserved by the operating system, except some regions that are reserved. Now the operating system can place these 4 pages, these 4 virtual pages anywhere in the physical memory. So VPN 0 can come here, VPN 1 can be here, VPN 2, and let's say VPN 3. Okay. And how does we need some mapping to keep track of this, and the data structure that the operating system uses to keep track of this particular mapping of which virtual page is placed where in physical memory is called the page table. Usually the page table is just like a single array. In this case, it's just an array of 4 entries. Okay, just an array of 4 entries, and these 4 entries are just VPN 0. This is entry for the 0th virtual page, entry for the 1st, 2nd, and 3rd. So VPN 0 is placed in 5. So numbers 5 would be here. Then VPN 1 is placed in the physical frame 7. Then physical frame 2 is placed in 4 and 3 is placed in 2. Okay? Usually this is how a page table looks like. It just has the mapping. One more important information that this page table contains, this part that we saw till now, is called the page frame number. Okay? It's called the page frame number. It's right here. Does any of you know like why this is happening or something?
Maybe try turning off autofocus.
Pen is too bright.
Pardon?
Yeah, there's something about the contrast of your hand or the paper.
Oh,
Change the saturation.
so do you know how to do it? If anyone has any idea how to fix it,
Can you
please help me.
can you put the end of your black pen under just the black pen? And what about when that label faces the camera?
When the label,
Yeah.
What do you think that's could be?
Well, maybe.
with my
It's your
Oh, it's your
Ring.
ring.
Sorry.
ring.
maybe.
Try taking your ring off.
It's my wedding ring. Yeah, really, like, it's just fun fact, I just like got married 2 weeks before the first class I took here. Yeah. Thank you. Thanks. And one more fun fact is like my wife is coming to the US tomorrow. She's in India currently, and she's like coming here tomorrow. And I'm so excited about it. Okay. Okay, let's try now. I just removed my wedding ring, but still it's happening. Maybe my finger, my nails.
Maybe try keeping your hand like on the side rather than the middle.
Here,
Or you can just.
how can I write?
off.
Okay, let's just try this. Okay, and one more bit, one more information that we need here, okay, in the page table is called the valid bit. In our case, since we have like all the four, let's assume in this case we have all the four pages here are already placed in the physical memory, which means that all these bits should have been of value 1, because if one of these bits, so for example, let's assume if this bit's value was 0, if the second page says that it is currently invalid, all this means is this page is a free page. Okay, this page is a free page, and so the operating system will not even allocate any space for it here. This will not be here. Okay, the operating system will not even allocate any space for the free page in the physical memory, and so your page table will look like this. And so I think if you have completed the first problem in the worksheet, this was like you go and find the valid bit in a particular page table entry, and these entries, all these entries are called page table entries. This is like one page table entry. Okay, these are called page table entries. So in each page table entry, you find the bit that is corresponding to the valid bit. If it is valid, then it means that that particular virtual page is actually has some code or data or stack or heap, and it is currently in the physical memory. It has some space occupying in the physical memory. If it is invalid, it just means that this particular virtual page is free and it is unallocated. And so since it is unallocated, it would be wasteful of using the memory in the physical memory, and so we will not even have that particular virtual page allocated in the physical memory. And if someone tries to access this particular virtual page, some address within this particular virtual page, so for example, addresses 32 to, in this case the virtual addresses 32 to 47 lie within this particular virtual page 2. If someone tries to access any address within that range, then it's going to give a segmentation fault. The operating system is going to kill that particular process. Okay. And this particular page table that we have here will be stored in the physical memory. Okay, let's assume this is stored in the physical memory, and usually it has a starting address. Like assume the start address is 0x. Let's assume it is stored at like some hex 1000 or something. Or for simplicity, let's just assume it to be just the decimal 1000. Okay, let's assume this is stored at some address like 1000 in physical memory. When this is so, when this is stored like this, whenever hardware gets a particular virtual address, so this is the format of the virtual address. So let's assume we will try to access some virtual address in the format 0111011. This is the virtual address that we are trying to access. Okay, then the hardware just tries to figure out what is the virtual page that this address belongs to. It's like the first virtual page, and now the hardware, okay, whenever an address translation happens, usually the operating system does not get involved. Okay, so if the operating system does not get involved in an address translation, then the hardware needs to figure out how can it access this particular value of 7 from this page table. Okay, and the way the hardware does this is it has this particular address, the starting address of this particular page table in a register called a page table base register. It's called PTBR. The PTBR currently will have the address of 1000, which just means this register is a pointer to the starting address of the page table. And so whenever the hardware gets this address, we really don't know what this address is, but we just found that it is trying to, this address belongs to the virtual page 1 or the first virtual page. So all the hardware does is takes the value from this PTBR, okay, which is 1000, then just adds the virtual page number component to it. So the virtual page number currently is just 1. Okay, the value of the virtual page number is just 1, and it just multiplies the size of each page table entry, because it starts at address 1000. If, let's assume in this case, if each page table entry, if a size of one page table entry, if it is 2 bytes, if we assume that each page table entry is of size 2 bytes, in this case, then the hardware needs to go to the address number 1002 to access the virtual page table entry for the first virtual page. Does it make sense? So all it has to do is just say page table base register plus the VPN times the size of a page table entry. So in the example that we are seeing, the size of page table entry is 2, the VPN number we are trying to access is just 1, and so this will give you the actual the page table entries address. This particular thing will give you the page table entries address. In our example, in our example, this address is nothing but 1002, because this particular page table entry, the second page table entry, is present at the address 1002. Does this make sense? This is how the hardware tries to figure out where the particular page table entry is.
You were going to tell us why it's called the physical frame number?
So, you mean why have they named it like that?
Yeah.
So, we have, okay, the question is, why are we calling this the physical frame number? So, I think this is just my guess or something. I think they just like split the whole physical address into like some page-sized chunks, and the other name, okay, there are multiple names for this. This is the name that we are just using in this class. One more name for this is like physical page number, PPN. So it's the page number in the physical memory. We are trying to avoid that particular thing just to be very clear about what we are talking about. And so I think there are just like names for the particular chunks of memory that we have. Any questions about how are we calculating this? Okay, great. Okay, yeah.
Shouldn't the first virtual page be 0? Like why we use 1 for this 0? Shouldn't it be 0, 0, 1, 0, 1, or 1?
So the first virtual page is still 0, in the sense it starts at 0. So we have like the VPN 0, the VPN 1, VPN 2, VPN 3. But the example that we just took here, the example that we have here, the 2 bits that represent the VPN was just like 0, 1. And so for example, let's try to just convert this to be very sure. Like if we try to convert this to a decimal number, you can figure out like this is like 1, 2, 4, 8, 16, right? So 16 plus 8, 24, 26, 27. So this is nothing but 27 in decimal. And if you see here, it would just fall under the first virtual page, virtual page 2.
Sorry, when you were, I just had the first, never mind.
Okay, makes sense. So, yeah, with this, now we have this page table base register, and one important thing that happens is whenever a context switch happens, okay, on a context switch, the current value of page table base register is going to be invalid, because let's assume this page table only belongs to or is the page table for process 1. When we are going to execute process 2, then for example, if we have like, let's say this is the page table base register's value of 1000, and we can assume that P2's page table, okay, P2's page table is in the address 2000 in physical memory, okay, because it's a completely different set of translations for from the virtual pages of P2 to where it is allocated in the physical memory. And so whenever a context switch happens, the operating system is going to change the value in the page table base register to the page table of the corresponding process that we are switching to. Does it make sense? So this is what is happening here. And now one concern that we have here is, now let's just think about a simple instruction like move. Okay, a move instruction which is at address, let's say 20, and it says like move the move something from address like 100 to EAX. If you remember, we started last class by asking like how many memory accesses, how many physical memory accesses are required for this particular instruction. Okay, and at the time we were not considering paging, and at the time we told like it was like 2 memory accesses. If you remember, there was 1 memory access needed to go and fetch this particular instruction at for simplicity, let's assume both to be in hexadecimal, to go and fetch this particular address at 0x20, and then the second memory access was to go and get the data from this particular address. Okay, but with paging, can you think of like what will be the total number of memory accesses for this particular statement, for this particular line of assembly code? So we are still assuming we just have a single linear page table. The assumption is we have a single linear page table. Exactly. So we need like 4 memory accesses for this particular thing, because to know where this particular instruction is in the physical memory, we need like 1 memory access to the page table entry of this code page. This is just a code page, right? We need one access to the page table entry. The 4 accesses are, the first access is page table entry of the code containing the address 0x20. Okay, then the second memory access is just accessing the address, accessing the physical address that is corresponding to the virtual address 20. Okay, then the third memory access is going to be accessing the page table entry for, let's assume this is in data section, for the data section containing the address 0x100. And then the last thing is going to be the actual physical address that is corresponding to the virtual address 100. These are the 4 memory accesses that we need to access a single instruction like this when we are using a simple linear page table. Does this make sense? And so what we are actually doing is, if we are accessing memory like in this way, then just think about it, we would slow down, okay? We would slow down our program by 2 times. For each memory access, now we need twice the amount of memory access than it was required previously, because we have some structures in between, like the page tables, where we store like crucial information about the mappings of the virtual pages to the physical pages. So we need to access those page table entries first in turn in order to access the actual physical memory. So this is definitely not going to be acceptable. And so let's see what is the solution for this. So first, before going on to the solution, let's just try to summarize whatever we just saw right now. Okay, how do we access memory? You may assume that small instruction. So whenever we are going to access memory, we are going to, the first thing is so let's assume whenever we are accessing memory, we are given the virtual address. Okay? We are given the virtual address. So what are the steps that the hardware is doing currently for accessing memory is, it just extracts the VPN virtual page number from the virtual address. This is the first step. Then what are we doing next? After we extract this VPN from the virtual address, immediately we just calculate the page table entry address using the page table base register and the VPN. We just extracted the VPN times size of the page table entry. We calculate this. Now using this particular address, you go and access the physical memory. So you get the page table entry. You get this page table entry by accessing the physical memory at this particular address, page table entry address. This particular thing is an expensive operation because it is a memory access. So now let's assume we got the PTE. Now the hardware has the page table entry. And we know that a page table entry will look like, let's say this. As we know now, the page table entry will just look like a valid bit and a PFN. Now what should the hardware do in this process? What would be the next step that this hardware does? The hardware just first checks this valid bit. Okay, and if we can assume, as of now, we can assume that it is valid page, then if it is a valid page, then the hardware is going to extract the PFN. It needs to get the page frame number from this PTE. Okay, and once the hardware gets this page frame number from this PTE, what is the hardware going to do? Let's assume now we have our page frame number. So if we have our page frame number, let's go back to this example that we were looking. Okay, if this is the virtual address that we are trying to access, the page frame number is nothing but we have the virtual page number 01. Okay, we go to this particular virtual page. This is the page frame number. Now you got the page frame number, which is nothing but 7. Okay. Now 7 can be represented in, let's say, 3 bits, 1, 1, 1. Okay. If you have this page frame number, all that the hardware is going to do is append. It's just going to append the offset directly from the virtual address, because we found the virtual page frame. So the high-level idea here is, okay, so now we know that this is the virtual page that we are interested in, virtual page 1. And we also know that this virtual page is currently here at the physical frame 7. Okay, we are at the physical frame 7. Now all we need to find out, the only thing that is remaining is the address that we are interested in is somewhere within this virtual page. Let's assume if this is the address that we are interested in, if it is somewhere from at some offset from this virtual page, and this is the offset, okay? It's at some offset from this virtual page, and this same address is going to be at the same offset here in the physical frame. That's all we are going to do. And so since it is going to be at the same offset, all we are going to do is just take this particular offset from here as it is and just append it here. So it's just going to be 1011, which is the offset. Now if you look at this as a 7-bit number, because you need 7 bits because the total size of the physical memory here was 128 bytes, which was 2 to the power of 7. Okay, now with these 7 bits just represents, if you convert it to decimal or hexadecimal, or this is in binary, whatever it may be, but this address just represents the physical address that corresponds to this virtual address, physical address of this virtual address that we had here. That's all we have here. And so in this summary that we are writing, after getting the PFN, you just append the offset, and this will give you the actual physical address. And the last step is go and access the physical address. So I'm just modifying this notation. This is just like a memory access. Okay. So here also you're going to do another memory access of this particular physical address, and then this whatever value, like after accessing this, you're going to just store it in a register based on whatever example that we just saw here. Okay, and this is also an expensive operation, and this is also an expensive operation. These are the sequence of steps that happens currently whenever a single memory location is accessed. Okay, in simple linear paging. Now we already saw for each memory access we have this additional overhead. This is like really expensive. We have like 2 memory accesses, and to avoid this particular thing, most of the times, what do you think can we do? Or what? You guys have any ideas? Like what can we do to reduce the memory access from 2 memory accesses for each access to just 1? Yeah.
Store some of the page table on the hardware.
Exactly. So we can just store some hot parts or like some frequently accessed parts of the page table, which just has the mapping from the virtual pages to the physical pages. Somewhere else, like in a cache, you can have it in a cache so that the hardware can directly access it without the hardware can just access the frequently accessed page table translations or address translations directly from that cache instead of coming and doing a memory access. Okay, so we have this hardware here. Let's assume if this is our hardware and if this is the memory. Now the problem is just like coming to this memory to access like 2 things, like or twice for each memory access. Now, so just to make something clear, we can't do anything with this particular access because this particular access that we have here is the actual access to the memory location. Okay, so for this we need to go to the physical memory. Okay, and now, but what we're trying to do is we in our memory management unit, let's assume if this is our memory management unit, you can have some other like an address translation cache. You can have a special cache. This is like a special cache for just storing the address translations between VPNs and PFNs. This cache just says like for VPN number, let's assume for the example that we had, the page table, basically the page table's translations like 1 is mapped to 5, then 0 is mapped to 5, 1 is mapped to 7, 2 is not mapped anywhere, so it will not be here, 3 is mapped to 2. This particular translation, like if you assume that the page table that we had initially, this may have like many entries in it, okay, this may have like n number of entries, but this cache would be of limited size. By limited size here we mean this cache that we are talking here, okay, or the address translation cache. This address translation cache that we're talking here can only have limited entries like 16, 32, 64, or maybe maximum 512 entries. This will be the maximum number of entries that we have in this address translation cache. And due to historical reasons, okay, this particular cache is just named as the TLB. This particular cache, this address translation cache that we have here, for historical reasons, it's just named as translation look aside buffer, or translation look aside buffer. And now, okay, let's see how is this memory access, like the steps that we had here, how is this going to change with a TLB? So TLB again is a special type of cache that we have inside the memory management unit of our hardware, which can only cache address translations. So inside a TLB, you can't store any data or code or stack or heap. Like here, it can only store address translation. So it can only store page table entries, basically. Make sense? And so now, with this particular setup, okay, now let's see how does the address translation change. So any questions about this till now before we proceed?
Does the translation look-aside buffer also store whether they're valid or not?
Exactly, yeah. So we'll get into those details right now. So the question is, will the translation look-aside buffer store if this particular translation is valid or not? Okay. The question is yes. It has something called, along with these things, it has something called a valid bit. Okay. But this valid bit is totally different than the valid bit that we saw in the page table entry. Okay? The valid bit in the page table entry that we saw before says, is that page allocated or not? Okay? But this valid bit that we have here in TLB just says, is this particular translation valid or not? This is like different. We'll get into much more detail. This just says, so for example, this may be, okay, this particular thing, let's say, maybe like 1, 0, 1, okay. If this is, for example, if these are the 3 valid bits that we have in a TLB, just looking at this valid bit, okay, just looking at this valid bit, we cannot say that that page is an invalid page, okay? But all we can say with this particular valid bit of 0 here is this particular page, this particular virtual page 1 for this process that we're trying to do a memory like address translation is not present in the TLB. Okay? It just says it is not present in the TLB. So again, whenever a valid bit is 0 here, we will not even actually go and look at this information. Okay, I think this may be like more clear after we discuss a few things right now. Can come back to this.
Why is the size of the page table entry 2?
That's just like we just assumed it. Usually it is like 4 bytes. So in the previous example that we were discussing, we just like assumed the size of a page table entry to be 2 bytes. It need not be. It can be like 1 byte or like usually it is like 4 bytes. Okay, usually the size of a page table entry is 4 bytes. We are just assuming things. Any other question? Okay. So now memory access with TLBs. What happens to the same memory access that we are just seeing here, but we have TLB in our machine right now. Okay. The first thing again is the scenario is again you are given a virtual address. How can you convert this to a physical address and then access that physical address? First thing is the same. Extract the VPN from the virtual address. Okay. Then now what is going to change? So now we have this VPN. Now with a TLB, what do you think is going to change? We are not going to calculate the page table entry address immediately, but instead we are going to take this particular VPN, okay, go to our TLB. Let's assume the VPN that we are trying to, from this virtual address, if the VPN that we are trying to access is VPN 1, okay, we will go through this particular TLB to see if VPN 1 is present here, okay. Currently it is present, okay. Actually currently it is not present, okay, sorry. Because like even though we have that number here, we have the valid bit set to 0, okay. So first let's just check like check the TLB. If VPN is present, okay, if the VPN is present, for example, in these two cases, if we are checking for VPNs 0 and 3 in this case, if we are checking for VPN 0 and 3, both have valid bits set to 1, and so they are currently in the TLB, okay, both the address translations for these two things are currently in the TLB, and so this particular condition is called a TLB hit, okay. We have a hit in the TLB. And so whenever we have a hit in the TLB, it becomes like really easy because we already have the required physical frame number right here, which is such a huge gain because we need not go and access the physical memory, the page table, to get this particular translation. So for example, if we are trying to access some address with VPN 0, let's assume we are trying to access the address 0 itself, okay, or like address 1, something which is in the VPN 0, then we have got the PFN right here. You can just take that particular PFN and immediately you can form the physical address. Makes sense? So you have a TLB hit, then the case is get the PFN from the TLB, add it with the offset. By adding here, I actually mean just appending at the end, okay? Appending the offset to this particular PFN, which gives us the physical address directly, in the sense. We get the physical address, and now you can just go and access the memory. Access memory for this particular physical address, and you are done, okay? And it's done. So you just like reduced the memory access from 2 to 1, if it is a TLB hit, okay? Which is a great. But it's not always so. If VPN is not present when we are checking the TLB, okay, this is like case A, and case B is if VPN is not present. So for that, an example may be we are trying to search for, let's say, this virtual address 1, okay? Even though it shows that virtual address, that is the virtual address 1 here, this particular valid bit says that this particular translation is invalid, okay? But even before that, one important thing here is there may be a case that we are searching for, let's say, VPN 2, okay? And this TLB just has little space for having the page table entries when compared to the actual page table, so we may not be able to store the entire page table here. So it can easily be possible that only a few page table entries are actually cached here in the TLB, and so the VPN that you're searching for may not be even here, okay? That is one case. And one other case is like it shows that it is here, it shows as if it's here, but the valid bit says like it is not a valid translation. Okay, the valid bit just says that it is not a valid translation. Just with this, we can't make any assumptions about if the page is really a valid page or not. Okay, all we can like confirm or decide at this point is just to make sure that, okay, I just know that I don't have the corresponding page table entry for this particular VPN in the TLB. That's all we can know at this point. And so this particular scenario or this particular case is called a TLB miss. So when a TLB miss happens, now, okay, what are we going to do? Any guesses? If it is a TLB miss, what should be the next step? The only thing that we have till now is our VPN. Pardon? Exactly. So we have to find out, okay, is this, go and find out the page table entry for this corresponding VPN in the physical memory. So for that, first you have to calculate that particular thing, right? You have to calculate the page table entry address. And we already know that we can use the page table base register and just add it with the VPN number times the size of a page table entry, And once you do this, you get the page table entry address. And now, now you got the page table entry address. Remember what we did here. After we got the page table entry address, we just accessed that particular page table entry, okay? And we extracted the PFN from there and did like we just did this, right? So now in this case, okay, you go and access this page table entry, but here in this path, in the TLB miss path, okay, we are not going to, so okay, let's first just go get the page table entry. Get the corresponding PTE, okay, get the page table entry, and using this page table entry, now we are not going to calculate the PFN, okay, but instead what we are going to do is, we are just going to update the TLB with this particular page table entry. Okay, we are just going to, we got the page table entry, which is a translation for this particular virtual page. You just go and update the TLB with this particular page table entry. Get the page table entry and update the TLB with the translation. Again, this page table entry is nothing but it just knows which virtual page is mapped to which physical frame number. That's all. That's the important information that we have in this page table entry. Okay. And but one more thing. Okay, we are making some assumptions here. When we just went to that page table entry, if that page table entry was invalid, okay, if that page table entry was invalid, then we would not do this. Because if a page table entry's valid bit is invalid, then it means that it is not even a valid virtual page. So immediately it's going to be a seg fault. Okay? But here we are assuming that that particular translation is valid, in the sense that particular page table entry is a valid page table entry. And so we are just getting that page table entry from the physical memory and updating the TLB's content with it. We just add this particular translation to the TLB. Yeah.
Is it still a TLB miss if the valid bit is 0 in the TLB, and so it will still continue to look for it in the page table in memory?
Exactly.
Okay,
Yeah.
sorry.
So if the valid bit for a particular virtual page, if it is 0 in the TLB, then it is a TLB miss, and you'll go and look for that particular actual page table entry in the physical memory.
Is there a case where it could be 1 in the actual memory, but 0 in the TLB?
Exactly.
So
So
it's
that
not-
can easily be cases like that.
So
Yeah.
it's not updating the TLB when it updates the valid bits in memory?
No. So that's a very good question. Okay, the question is, can a particular page table entry have a valid bit of 0 in the TLB, but 1 in the actual page table? Yes, it is possible. In this case, it just means that that particular translation or that particular page table entry is not found in the TLB, but it is found somewhere in the page table, and that page table's virtual page is a valid virtual page. Okay? And so when we are updating, and so in that case, when you are updating that particular information, you are bringing this particular page table entry to the TLB. And so now, since it is going to be present in the TLB, we are going to update the valid bit of the TLB to be 1. So that we are saying like now the correct translation is present here.
I think maybe Rick probably explained why the valid rate is set to 0 in the first place.
Yeah, you go into that, yeah.
How does the hardware decide which page table entry to get rid of when it's updating one?
That's a very good question. So again, the question is, okay, the first question is, why does even a page table entry in the, or like a TLB entry in the TLB has a valid bit of 0, okay? I'm not going to answer that right now because we are going to look at that in a few minutes. Second question is, how does the operating system decide which TLB entry to kick out if it is already full, to go and place this new entry? And the answer for that is, again, we have cache replacement policies. We'll be looking at that, like in the next class, basically. It's like the policy side of memory management. And same question. Okay, so now we get this translation, update. The important part is like updating the TLB with that, okay? Updating the TLB with that particular translation, and then all we are going to do is just retry that particular instruction. Retry the same instruction. Okay, so when we are retrying the same instruction, what we mean here is the first time when the instruction tried to execute, like move 200, EAX, that particular virtual address, the particular address 200 was not in the TLB, but it was somewhere in the page table. Now we have updated in the page table, so now that instruction will be executed again. And so when that instruction is executed again, now we'll come here again, okay? It will be taking the path of it will extract the VPN from the particular instruction and see if it is in the TLB. It will be, because we just updated it right now. And so it's going to be TLB hit, and then we are going to extract the PFN, the offset, and calculate the physical address. And then access the memory with that physical address. Makes sense? Okay, till now I was just using like the pronoun we. We are doing this, we are doing this. Can you think of like all the steps that we just saw? Is this done by the hardware or by the operating system? Or a combination of both? Maybe let's keep it simple. Just think if it is just the hardware or the operating system.
Hardware.
Hardware? Can you like explain why? Why do you think so? If you have ideas.
It's all just stored there. So it's just moving its chart around. Just to
Great.
look at things and store it, registers, and then update things. Like you don't need OS to like govern any of that. That's all the information you need.
Amazing, yeah. So whatever we just saw here, okay, whatever we just saw here can be just done by the hardware. And usually, okay, in like olden times or like few years before, like this was just completely done by the hardware, okay? And whatever we just see here, we just extracted we are just trying to do some address translation. The TLB is part of the hardware, you can access it easily. The only tricky part is here, okay? For the hardware, the only tricky part is here, but it can easily go because it already has the page table base register. It just goes to that particular page table base register and extracts like the page table address, and then goes and updates its own TLB just in the hardware, and just reruns the instruction again, okay? So this whole thing can be done just in the hardware. But what happens is, this page table that we are talking about, okay, here, page table that we are talking about should be like in a very simple format, basically. And okay, the first thing is like this can be done whenever we are trying to handle a TLB miss, okay? This part can be done either by the hardware or the operating system, okay? Mostly, previously it was just done by the hardware, but later what happened was the page tables got more and more complex, okay? When the page tables got more and more complex, it was like the hardware needs to know a lot of information about the page table to actually go and, like, let's say, extract the PFN, okay, to extract the PFN and stuff from the page table. And so whenever we have a TLB miss, this particular part in this sequence of steps is just done by the hardware, but this whole thing that we have here for a TLB miss, okay, can also be done by the operating system, okay, can be done by the operating system. In that setup, all the hardware will do is, whenever it finds out it is a TLB miss, it will just raise a TLB miss exception. Very similar to whatever we saw with the, like whenever a system call happens, like it just raises a trap basically. It just traps into the operating system. And that is what we are going to see next, okay? So I think we can take a break right now. And after the break, we'll see like what happens when this TLB is managed by the operating system. let's take a 10-minute break or like operating system. Okay, manage TLB. So here the steps 1 and 2 are going to be exactly the same. Okay, so we're not going to do anything here. It's like the same from how we saw previously. So if it's a TLB hit, then everything is like done here. We just access the EFN directly from the TLB and form the physical address using the offset and access the physical memory. But if it is a TLB miss, so the case only gets interesting if it's a TLB miss. If it's a TLB miss, immediately the hardware just raises something called a TLB miss exception. It raises something called a TLB miss exception, which is nothing but a trap, okay, which is just like a trap. So initially when the hardware, the operating system booted, the operating system would have registered this TLB miss exception along with the, let's say, the timer handler, the system call handler, along with all those things, the operating system would have registered this also in that particular trap table. So this is just like one entry in the trap table would just point to this particular TLB miss exception, okay, or TLB trap handler. So now after this, we would just like the hardware would just like trap into the, let's assume this is the operating system, it just traps into the operating system, okay, and then the operating system just takes control. So all it has to do is like the operating system needs to run a TLB miss exception handler, run the code that does this, okay, and so when it runs the code that what is going to happen in the TLB miss exception handler, it's just going to check the page table. Now do we need the page table base register for accessing the page table? We really don't need, think about it, we really don't need the page table base register to access the page table because now the operating system is doing this and the page table is just data structure within the operating system. Okay, it can access it directly. And so the operating system directly accesses the page table for getting the page table entry. And now again, as usual, this is going to check, okay? Operating system is going to check if the valid bit, the protection bits are nothing but, as we saw previously in the last class, some virtual pages which contain only the code may have like protection bits as just read and execute. But the virtual pages that contain the heap and the stack will have like protection bits to be set to read and write. Okay, and so if all these things are okay, the valid bit, the protection bits, if all these things are okay, then what should the operating system do? And the operating system should first, as usual as we did previously, should extract the page frame number from the page table entry. Now we have the page frame number. Now what should the operating system do? As we saw previously in the hardware managed TLB, the hardware would just like update its own TLB using this page frame number, right? In a similar way, the operating system is going to update the TLB. Update the TLB with this, let's say, translation, okay? The hardware is just going to update the TLB with this translation, but it's going to be slightly tricky, right? How can the operating system update the TLB with this particular translation? What are the things that are required here?
Special instruction.
Exactly. Special instructions which are privileged. So we definitely need some new instructions or some special instructions that are in the that can only be executed in the privileged mode or in the kernel mode. Because if anyone is given the power to go and register or like update this TLB with a particular translation, just think about what a user program can do. It can even make all its translations be available in the particular TLB to make it faster. And so the instructions that are used for updating the TLB, okay, these are privileged instructions. Okay. And then now the operating system has done its part of handling a particular TLB. Yes. Now what would the operating system usually do in this case? Once we are done with the trap, what would be the instruction that is going to be executed? Remember the IRET, the special instruction return, IRET, which is just like the return from trap. We just execute a return from trap instruction because this is just a trap. Now you're returning back. Now, after this, the control gets back to the hardware. Okay. Now the hardware is going to execute something. Okay. When the return from trap happens, we are here. Okay. We are in the hardware. And once we are here, the hardware is going to execute. I'm afraid to just zoom out and just afraid that problem would come again, but yeah. So the hardware now knows that okay, the TLB miss has been handled. Now what should the hardware do? Should the hardware execute the current instruction or should the hardware execute the next instruction? Exactly, the hardware should execute the current instruction one more time, because only if it executes the current instruction one more time, we would be able to come back to this particular step again, where we can extract the VPN from the virtual address, and then it will be a TLB. It is going to be a TLB hit, okay? And once it's a TLB hit, then you can access the physical memory, physical address, okay? And so this is like a very important distinction between a TLB exception and a system call, okay? So let's just look at this right now. So the important thing is, let's assume there are like two instructions here, address like 1000 and address 1004. And if this is like a write system call, and if this is again the same address 1000, a different process, let's assume if this particular thing is move 200 to register EAX, and we can assume that this particular thing is going to produce a TLB miss. Okay, it's going to produce a TLB miss. In this case, this is going to be whenever we trap into the operating system, we have the write syscall handler here. The write syscall handler will execute. Okay, and once the write syscall handler executes, we return. So we do iReturn, and now we go here. After we return from a syscall handler, the instruction that is going to be executed is not the current instruction, because that was already done. That is already done. It is going to be the next instruction. So here it is going to be 1004. Okay. But if in this case, when we just trapped into the operating system due to a TLB miss, we are running a TLB miss exception. Let's say TLB miss exception handler. And after we run this TLB miss exception handler, now when we do a iReturn or return from trap and go back here, we are not going to execute 1004, but instead we are going to execute this particular instruction again. This is like a very important distinction between system calls and some types of exceptions. This is like a very important distinction between a system call and an exception. And so the hardware really needs to figure out, okay, whenever the hardware is trapping into the operating system, it needs to figure out, is it trapping due to system call or due to some other type of exception. If it is a system call, it just stores the current address in the program counter. If it is a, let's say, TLB miss exception, it will store the, if it is a system call, it will store the next address in the program counter. And if it is a TLB miss exception, it's going to store the current address in the program counter. Okay, this is like a very important distinction. What will happen, let's assume like in this case, what will happen if this exception was a protection fault? By protection fault, here we mean the program is trying to access some invalid virtual page. Which instruction will be returned to, or like what is going to happen after this? Protection fault, yeah?
Aren't you just going to kill the program?
Exactly. We are not going to like return to any instruction, any of the current or the next instruction. The operating system is just going to kill the particular program. Because if it's a protection fault, then the operating system has no way to continue that particular program after that. Okay? When an interrupt happens, in this case, let's assume when a timer interrupt happens, what is going to happen? Are we going to return to the instruction that was executing when the timer, let's assume the instruction at 1004 was executing when a timer interrupt just came in. Then once we go and handle the timer interrupt, which instruction will be returned to after handling the timer interrupt? Pardon?
The next one?
The next one, yeah. Usually what happens is whenever an instruction is executing currently, even when a timer interrupt comes during that time, the hardware will finish executing that particular instruction and then go and handle the particular timer interrupt, okay? And so obviously, since that instruction was executed, let's say in this case, since instruction at 0x1000 was executed, after coming back from the timer interrupt, we are going to execute the instruction at 1004, okay? Okay. Now, an important problem in this TLBs is, till now we were just assuming a single process was running and the process has some of its some of its page table entries that are cached in the TLB, right? So what happens when a context switch happens? So let's assume there is a context switch from process P1 to P2, okay? And currently the TLB's contents looks like this. Let's assume currently the TLB's contents just looks like this: a valid bit, a VPN, and a PFN. Let me assume like some numbers here, okay? P1, 2, 0. Something like this. If this is the contents of the TLB currently, and you can assume that all these virtual pages just belong to process P1, okay? Whatever is being currently cached in the TLB just belong to process P1. We can assume, make that assumption as of now. Now can you think like, okay, if there is going to be a context switch currently, what should happen here, or like what? Because let's assume when process 2 starts executing now, none of these translations are going to be valid for process 2, right? Because process 2 has its own page table and the translations are going to be completely different. So any ideas like what we can do here?
Just set the valid bit to 0 for all of the translations.
Exactly, that's like one of the easiest ways to do is whenever a context switch happens, just do a flush, okay? Flush means just clean all the entries in the TLB completely. And so for doing that, all we do is just go and set the valid bits, set all the valid bits to be 0. So that, and this was one of the reasons like why there can be like the valid bit set to be 0. This like one of the reasons is like, okay, now all the valid bits are set to 0. And now, when the second process starts executing, a few of its translations now would occupy the TLB, and so some would be valid translations. Let's assume if only the first two entries are for, so let's assume, okay, this is there, okay, now the TLB will become, after this, we will just go and set all these things to 0 when you're going to do a context switch. None of this is like invalid, none of this is valid, sorry, none of this is valid, and so now when process 2 starts executing, let's assume as of now process 2 only needs like just two virtual pages. It's just accessing two virtual pages. In that case, it may use this particular page. So virtual page 2 can be mapped to 7 for process 2. Then it is maybe using this particular entry also, with valid bit 1. Virtual page 3 is mapping to PF and 8. But the other two things would still remain to be 0. And when it is 0, we need not even worry about these particular entries here.
Is the page table stored in the process control block?
Pardon?
Is the page table stored in the process control block in the OS? I was just curious.
Yeah,
if the OS
exactly.
knows.
So,
Okay.
so question is, how does the OS know where each and every page table is? So we saw the PCB or the process control block, right? Each process control block will have a pointer to the page table. Okay, so all the OS needs to do is go to a particular PCB for a particular process, get that address and access that particular page table. So here in this case, so now after we switch to P2, this may be the situation where two of the entries in the TLB are valid and the other two are invalid. Okay, but this is a working solution. There is no problem with this. But what are the things that we need to make this work, to make a flush work? Yeah. Exactly. We need an additional instruction for the operating system to perform this flush, which needs to be a privileged instruction again, because we are accessing an important structure in the hardware called the TLB. Okay, so operating system, the hardware needs to provide a new instruction for this. And so let's assume in that case we are making assumption that the operating system is managing the TLB. Okay, if the operating system is managing the TLB, then this may be the case. We need additional instruction. What do we need? Or like if the hardware is managing the TLB, as you saw previously, the hardware can also manage the TLB. If the hardware is managing the TLB, how do you think can the hardware make this flush work? Yeah, exactly. So one of the answers is like, okay, we can maybe flush the hardware can maybe flush the TLB whenever we return from a trap, okay? But that would not work completely because a process that went to a system call the OS may just decide to stay there. For example, if that is the only process that is running, even though we are returning from a trap, that may be the process that is going to be executed next, okay? In that case, unnecessarily we may have flushed the TLB, and just remember, once the TLB is flushed, again you need to bring back all those page table entries by accessing the memory, which is like unnecessary waste. So any other ways do you think the hardware can achieve this flush? So one other way, easier way for the hardware to do this, it has its own register called the page table base register, right? So whenever the contents of the page table base register is changed by the operating system, okay, the operating system changes the page table base register whenever a context switch happens. Because for each and every process, we have its own page table. And so the hardware can just use that particular signal of changing that particular page table base register to flush the TLB completely. Makes sense? This may work if there are like only few processes running and if context switch happens like only infrequently or something like that. But as we saw, like usually context switches happen so frequently among processes, and there are like n number of processes that are running, right? And so this may be an unnecessary overhead, this particular solution, since we are like bringing all the needed virtual page, like the translations, the PTEs to the TLB, and immediately we are like, whenever a context switch happens, we're just flushing it off. So are there like any other ideas? What can we do? Some other solutions? We have one more solution. So the other solution that we have is like some support that is provided by the hardware. Okay, in the TLB, what the hardware does is it provides an additional field in the TLB called an address space identifier, which is very similar to a PID, like a process ID. So now what happens is with this particular solution, the TLB structure now looks like this. You have a TLB, you have the valid bit, you have the virtual page number, you have the physical frame number, and along with that you just have like more bits called AS, one more thing, not a bit, it's like a field. Okay, you have one more field called ASID. So now your TLB can have mappings like this. One, let's say let's assume all the 4 things are valid as of now. The VPN of process, the VPN 3 and 5, and these are also VPNs 3 and 5. It can be there, okay? And the PFN is like 7, 8, 9, and 7. And the ASID is, this is, okay, first what the thing that we're doing here is just having a separate field to specify which processes, virtual pages are we talking about, okay? And then having all the other things as it was previously, okay? But can you just take a look at this particular TLB and can you think if this can be, if these contents that we have right now, can these be valid contents within a TLB?
No.
No? Why?
Two processes can't share the same physical, or like have the same like valid reference to the same physical frame.
Yeah, so one thing that we are seeing here is like the VPNs 3 from process 1 and the VPN 5 from process 2 are both having the same physical frame number. It is not actually, this is possible, okay? This is possible, which just means that, okay, this is not bad. This process 1, P1's some virtual page, okay, which is the virtual page 3, and process P2's another virtual page, let's say virtual page 5, both are actually in the physical memory, both are just mapping to the same physical frame called 7, physical frame 7. And in this way, okay, this particular physical frame is shared between these two processes. Okay, this is like a shared page, basically, shared physical frame. Yeah.
So is that what would happen if you had multiple processes running the same code?
Exactly, yeah.
What other situations would you have that?
What are situations other than that? Okay, one of the questions here is like, okay, this would be the scenario if we are running, let's say, two processes, P1 and P2, which have the same code in it. Let's say we wrote a program called P1.c and just ran like these two processes from the same code, okay? Then both these processes, code segments, are going to share the same physical frame in physical memory. The question was, okay, but the question was, what other situations this may happen, okay? And this shared memory, one of the most useful use cases is for doing like inter-process communication. We have like a shared page, okay, shared virtual page, I mean like a shared physical page in the physical memory. And this physical page would be like a spot for performing like communication between two processes. If you think of it currently, two processes have their own address spaces. There is no way that these two processes can communicate, and so this is like a mechanism. At least in the last summer when I taught this course, implementing something related to shared memory was the project for like the Linux part of memory management. They were like, students were implementing, not implementing basically, but they were like using the shared memory APIs that Linux provides to make something like this work, to perform inter-process communication. Again, if you think about it, whenever we are talking about two things are trying to access the same memory, what problems may arise? Exactly. So if two processors are trying to access the same memory locations, we need to make sure that the particular, that is like a critical section. So we need to lock that particular critical section or like this particular region of memory to make sure that only one of them write at a time. Okay. And like in like 2 classes or so, we are going to like just jump into like concurrency, which will be much more interesting. About like how can we do these things in much more detail. Okay. But yeah, this is not wrong because of this, because this is possible. And usually this happens whenever 2 processes, whenever if let's assume P2 is just a fork from P1. In that case, when P2 is just a fork from P1, then all the physical pages are just going to be shared in the physical memory because it just creates an exact replica of it in the virtual address space. So it's just going to point to the exact same things in the physical memory, but only when, okay? But only when, let's say, P2 makes some changes to some variables on the stack, okay? Only then at that time, that particular, let's assume, if both are sharing in this case, okay? And let's assume P2 is making a small change here, okay? This is like a different scenario, okay, where I'm thinking about forking currently, and after a fork, if P2 is changing some particular information here in this case, then after that we can't share this virtual page. So whenever this starts to write something, okay, then this virtual page will be copied, this physical page will be copied somewhere, and so let's say this is 9 or so, and then this now hereafter this will be using a new physical frame, and this will be using the same old physical frame. Okay, this particular technique of copying physical pages only when they are actually returned to is a very common technique in systems, and it is called copy on write. Called copy on write. Only when you do a write to some shared page, just make a copy. Again, this use case is a totally different use case than whatever we were just talking till now. Okay? When 2 processes are using a shared physical frame for inter-process communication, for communicating between them, we are not going to do this, okay? We are not going to do a copy on write. But this situation that I'm saying right now is just after a fork, if 2 processes are pointing to the same, but after a fork, this may not be valid because it will be like 3, the virtual page 3 will be the same in both the things, okay? After a fork, this will be 3 and this will also be 3, if they are pointing to the same physical frame. And then if something changes, then you copy that particular thing so that you can have the changed value in this new location. Something like this. And this particular technique is called copy on write, okay? Now, we were here, we just saw like what are the different ways to solve this. This is like a other way to solve this particular thing. Okay, any questions about, and this is how we solve the problem of the speed, in the sense the paging, simple paging mechanism was like very slow and compared to without the mechanism that does not use paging. So this is how we really solve this particular thing using TLBs.
When you copy it, do you update what the physical frame number is, or do you just void it, and then next time it has to come back and re-update in the TLB?
So,
Like, would you change that 7 to a 9, or would you change the 1 to a 0? What happens, I guess?
so when you copy this, you would go back. So this in the TLB, it will just like invalidate that particular page. It will make them invalid. But that particular entries, like 5 is mapped to 9. That particular information will be updated in the page table entry of P2.
Right. Yeah, but you invalidate the TLB, and it just sort of.
Yeah, exactly. And then when it is accessed the next time only, it will go and update the TLB. Again, we will not go into like, these are like far more details than what we need, but just like I thought this was like the question was a very good place to actually introduce this particular idea. Okay. Okay, and hence we have solved the problem of speed. Like now paging can be much faster than what we were doing previously. Any other questions? Because next we are going to solve the next problem. So now the first problem of speed was using TLB, solved using TLBs. maybe I can ask this question right now. How many of you felt that you learned something more than you learned in 354 till now? Okay, how many of you felt otherwise, that you have already maybe know almost all the things that we just discussed? Just raise your hand. I'm not going to like do anything, just like make a sense. Okay. Then I think we are good. Like, sorry for you guys here. But maybe now this may be interesting, the next part may be interesting. Okay, so we just solved this using the TLBs, and we are going to solve this problem, okay, of space. Okay, first let's see what is that problem. I think we already saw, I gave you like a high level introduction to that particular problem. Okay, now the problem of space. So we are usually considering like very small address spaces, but we also saw like in the real world we will have like a virtual address space. Okay, usually a virtual address space is of size 4. So virtual address space will be of, like in the 32-bit machine, it will be like 32. I think I'm messing this up. 1 second. So in a 32-bit machine, I'm just trying to write about 32-bit machine. Okay. In a 32-bit machine, we have 32 bits to represent a particular address. Okay. 0 till 31. We have 32 bits to represent a particular address. And so since we have 32 bits to represent a particular address, the maximum number of addresses that we can access in a virtual address space is 2 to the power of 32 bytes, which is nothing but 2 to the power of 2 times 2 to the power of 30 bytes. And this is nothing but 4 gigabytes. 2 to the power of 30 is giga, so 4 GB. Okay, the virtual address space is 4 GB in a real world machine. And page size in a real world machine will not be usually in the things that we are seeing in this class, like 16 bytes or something like that, but a page size usually is like 4 kilobytes. Okay, and these are the real world parameters that we have. Let's just assume we are still using a simple linear page table. Okay, if you are using simple linear page table, then with this particular thing, we are saying we have a virtual address space from 0 till 4 GB. The maximum possible address will be 4 GB minus 1. And this is split into pages of size 4 KB. Just like VPN 0, then VPN 1, stuff like that. Okay. We are just going to see how many virtual pages there may be, or what is the maximum number of virtual pages that we have in this setup. So in this setup, the number of virtual pages that we have is just the size of this total address space, which is 4 GB, divided by size of one page that we have, okay, which is 4 KB. And as we already saw, this just becomes, this is K and G, if you cancel this, it just becomes like 1 MB. Okay, because this is like 2 to the power of 30 and this is nothing but 2 to the power of 10. You get 2 to the power of 20, which is like approximately, approximately you have like 1 million pages. Okay, approximately you have 1 million virtual pages. Or exactly you have 1024 times 1024 virtual pages. Okay, if that is the size that you have for each thing, now, okay. So you have 1024 times 1024 virtual pages. Actually, I should not write it like a B here because B also will get cancelled with 1 M. Okay, 1 M virtual pages. It's approximately 1 million virtual pages. If we have 1 million virtual pages, let's just think about if we are having a page table for this particular setup. In this particular setup, if you have simple linear page table, the entries are going to be 0 up till the maximum entry or like, let's say you can start from anywhere, but the maximum entry in the page table, let's assume this is 0, okay, this is 1. In this case, the maximum entry in this page table is going to be 1 million or 1024 times 1024 minus 1. You have like so many entries, okay, and if each entry in this particular page table, this is like 1m minus 1 entry, and if you have like, if one entry is of size 4 bytes, okay, here we are assuming, because this is the real world setup, in the real world setup, one page table entry is usually of size 4 bytes. Okay, if one particular entry is of size 4 bytes, just for storing a single page table for a process, we need one page table needs 4 times, okay, because 4 bytes times 1 MB. Because you need like 4 MB for storing a single page table. Just think about, it's like very common for running like 100 or thousands of processes at the same time. If 100 processes are running, for 100 processes, we need like 400 MB. For 1000, need like nearly 4 GB or 4000 MB. So we need like this much space, okay? We need a lot of space. If we're using a simple linear page table, we need this much of space to actually just to store the page table. So this definitely is a problem. Does this make sense? Just want to like understand if the problem is clear before we proceed to the solution. Okay. The problem is, if we use a simple linear page table, we need a lot of space to just store the page tables for each and every process. And if it is 100 processes, we need like nearly 400 MB just to store the page table, which is like really huge, because there can be systems that have just like 1 GB or even 2 GB of main memory. In that case, you are occupying a lot more memory. Okay. Now, what may be like the solutions? Let's think about like a simple solution first. So, if you think about it, the main problem here is we have like these many entries. We have like these like 1 million minus 1 times entries. But how can we think about reducing the number of entries in the page table? Because that can be definitely one of the easiest solutions. Or how can we reduce the number of entries that we have in the page table?
Make pages larger.
Exactly. So we can reduce this number of entries in each page table, or the number of page table entries in a page table, by just having larger pages. By just having larger pages, what we mean here is like instead of having a 4 KB, what if we change this page size, okay, what if we change this page size from 4 KB to let's say 16 KB, okay? If we change this page size from 4 KB to 16 KB, then now we have a very big pages, and so the number of page table entries that we need is just like 4 GB divided by 16 KB, which is going to be 2 to the power of 20 by 4. This 2 to the power of 18, right? So we just reduced the size of the page table. So 2 to the power of 8 is 256, okay? 256 KB. So we just, by making a single page from 4 KB to 16 KB, we just reduced the size of the number of page table entries in the page table, okay? From, we need not worry about this KB because we are talking about the number of entries, okay? From 256, sorry, we just reduced it from 2 to the power of 20, which was like 1M, to 256K, which is 2 to the power of 18. Okay? But are there any problems with this?
You end up with more wasted physical memory.
Exactly. So we are again going back to the problem that we are trying to solve before. Okay, the problem was, now if we are going and loading, if we are just using let's say 1 KB of space in a particular page, Okay, even though you're just using a single 1 KB, you are wasting the remaining 15 KB of space in the physical memory because each and every page is of size 16 KB. Does it make sense? It's very similar to loading the entire process or loading like an entire segment of code, data, or stack here. Okay, so definitely this has advantages, but the main disadvantage is internal fragmentation within a single page. In this case, since the page size became so large, now within a single page, only these may be actually the used pages, and these may be free, and so in turn they are actually wasted. If this whole thing is just 16 KB in size, okay? This is like internal fragmentation is the problem here. Okay, so if this is a problem, then any other solutions? People like thought like, okay, we already saw first initially we were using the base and bones approach, and the way we made it better was using, what was the next approach that we saw after base and bones? Segmentation, exactly. So we used segmentation. Now can we use our the idea of segmentation again, okay, and just combine it with paging and see if we can come up with a better solution. This is like a hybrid approach, okay? This is like a hybrid approach between segmentation and paging. And the idea here is like very simple. So you have your virtual address space. Now we still have the idea of segments, which means we still have like, let's assume we have these things, okay? We have a code segment, we have a heap segment which goes up, we have a stack segment which goes down, okay? And let's assume this is like free or like unmapped region, okay? If this is how we have, then the idea here is, can we have like 3 different page tables, one each for each segment? So let's try to explain this idea. So here we are talking about, can we take this particular segment and just have like a page table for it? Like this is like a page table for code. It will have its own page table entries, okay? In a similar way, you will have a page table for heap, and you will have a page table for stack. Something like this, okay? The idea was like, can we do something like this? Just want to like explain this more with a specific example, okay? Okay, so in this example that we are going to see, okay, let's assume a few things, okay, to make this more clear, okay, why this is useful. Let's look at a simple example. So we have a virtual address space of size 1 KB. Okay, we have a virtual address space of size 1 KB. Let's assume a page size to be 16 bytes. Okay, and we can also assume size of a single page table entry is 2 bytes. Okay, if this is the setup that we are going to see, in this setup, let's see how this hybrid scheme of segmentation and paging is going to help. First, let's just see how many bits we need. We need 2 to the power of 10, just 2 to the power of 10 bytes, so we need like 10 bits, right? So a single virtual address is going to be represented using 10 bits. Okay, we have 10 bits now. The whole idea here is, now we have a page size of 16 bytes, which is nothing but 2 to the power of 4 bytes. So we need again 4 bits for the offset, right? Because from this you will just figure out the offset. So you have like 4 bits for the offset. Now usually these remaining bits are there, but since we are going to use a scheme of using both segmentation and paging, we are not going to use this entire thing as a virtual page number, but instead what we are going to do is, since we have 3 segments as of now, code, heap and stack, we are just reserving the topmost 2 bits as segment selectors, very similar to how we did with segmentation. You have like 2 bits for segment selectors, and then the remaining thing that we have here would be your VPN. Okay? Or this would be like, this is more like, this whole thing is the VPN, okay? This whole thing is the VPN, but after you found out which segment it is, this particular page falls into, you will use this as an offset within that particular segment. Okay, just to make sure. Okay, this whole thing is the VPN. Okay. Now this will be like the offset within that particular segment. This will be like an offset. I'm not naming it anything right now. I'll try to explain it and then we can come up with a name for this. This particular thing is just an offset within that particular segment. So if this is the scenario, then we know that code heap stack, we're going to have like 0, 0 for code, 0, 1 for heap, and 1, 1 for stack. Okay. And in this setup, the actual address space will look something like 0 till 1 KB, and this already divides this entire address space into 4 equal parts, okay, because we have this segmenting thing. So now we divide this into like, this is for the code. So code is going to have from 0, what is going to be the maximum address that we are going to have in the code segment? It's just going to be, since these 2 bits are segment selector bits, okay, the maximum that we can write in a 8-bit number is going to be the maximum address in the code segment, which is nothing but 2 to the power of 8 is 256. So it's 255. So code is just going to have from 0 to 255, or you can think like 256 is the start of the heap segment. Okay, this is the code, this is the heap. Heap is going to, then this particular place is going to be 512. And this is going to be something. So this is going to be the last valid address is going to be 1023. Okay, and that is going to be the stack. Now we just have this segment in memory right now, but we are going to divide each segment into pages. That is the main idea here. We are going to divide each segment into pages. So now a page segment, the code segment is going to have in turn like some pages within it. So something like this is the virtual page number 0. This is the virtual page number 1. Up till how many virtual pages? What is the maximum number of virtual pages that the code segment has? It's nothing but the maximum thing is 256. Okay, 256 is the number of addresses in the code segment. You divide that by the page size. Okay, divide that by the page size. 16 is 2 to the power of 8 by 2 to the power of 4. So you get 2 to the power of 4 or 16. So you have, this is the number of virtual pages in, let's say, a code segment. This also applies to every segment. Okay, so you have 16 virtual pages in a code segment. So it starts from 0 and it runs till 15. Okay, so 16th virtual page will be in the heap and it will run till 31. So 32 till 47, and the start here it will be 48 till 63. So now this is how, like, so now this is also again segmented into pages. And again, this is also again segmented into pages. Okay. So in this setup, okay, let's assume, as of now, let's assume only 3 virtual pages are valid. Okay, the valid virtual pages in this setup, the valid virtual pages are just like 0, 16, and 63. Okay. if these are just the 3 valid virtual pages, then in this setup, okay, how much memory do you think is needed in the physical memory for making this program run? So for making this program run, now we have only 3 valid virtual pages. 0, the virtual page 0 is valid, which is in the code segment. Virtual page 16 is also valid, which is in the heap segment. And virtual page 63 is also valid, which is in the stack segment. Just think about how many virtual pages do we need, how much physical memory do we need to actually execute this particular program. So in this setup, okay, maybe some more details. We are going to have like similar the base and the bounds. Like there is going to be like a base register, bounds register. So in this setup, this base and bounds will just correspond to where is the, or this is not exactly the base, but yeah, you can think of this as yeah, it is the base, but it's like the page table base register. Okay, it's the page table base register for, like there are going to be 3 page table base registers currently, 1 for the code, 1 for the heap, and 1 for the stack. Okay, because you have 3 page tables here, so you can have like 3 different page table base registers. Okay, and let's assume, as of now, let's assume some values. Okay, base of code, let's assume if this is the segment, if code is at base 0, like 1000, then 2000, then 3000, these are the locations where these things are there, the page tables are there, this is the heap and this is the stack. If these are the locations, now the bounds value here, okay, in this particular setup, in this hybrid scheme, the bounds value is not going to be the maximum, like the what was the bounds that we saw there? The bounds was the maximum size of valid addresses that this particular process can access, right, in code, stack, and heap. But in this setup, they usually have something like, just like code. In our example, we only have 1 valid page in code. So code is just going to have value of 1. That's just like 1 page table entry in the code's page table that is valid. And in this particular scenario, we will just have 1 in here also, okay, 1, 1. But let's assume we can have like a setup where the virtual pages that are valid are 0, 1, 2, 16, 17, 63, 62, 61, 60. In this case, okay, in this particular setup, now the valid bounds is going to be 3, for the heap is going to be 2, and for the stack it's going to be 4. This is how this is going to look like. Okay, but what it means really is we are having these 3. All these are page table base registers, and this is for the code, this is for the heap, and this is for the stack. Okay, and we are saying now this is pointing to some page table. Starting, this is like a page table. Okay, page table for the code, and it has only 3 valid entries. Entry 0, 1, and 2 are valid. This is pointing to some page table which has only 2 valid entries, 0 and 1. This is the page table for the heap. And here we are going to point to like a stack which has like 4 valid entries. So, in this case, okay, even though all these 3 segments individually have like a total of 8 or I think 16, right? It has each segment has 16 pages. Since they are not allocated, using the scheme we can easily reduce the amount of space that we are going to use in a page table. Does this make sense? Does this? So in this case, even though, I'll go back to this previous diagram, even though a single code, entire code segment is has like 16 virtual pages, we are only allocating 3 entries because we are assuming only the first 3 virtual pages in the code are valid. Only the 2 virtual pages in the heap are valid, and only the 4 virtual pages in the stack are valid, and so we are only allocating memory for the page table as needed. We are not having all the entries there.
Do you have to combine both splitting it up to have different page table big entries and only including the valid entries? Could you have one pointer to a table that only included valid without splitting it?
Exactly. So the question was like, can we just have like instead of having like separate page tables, just like a single table that has like contents of all the valid entries? We can definitely do that. That would be just the next way. Any questions about this particular scheme?
If you needed to add memory, or let's say you need to add something to the heap, would you have to copy like your entire page table over to one with more allocated space for it?
So let's assume currently the heap has 2 pages here.
Yeah.
If in the physical memory it has no space in that particular region, then the page table will be copied to a new location where it can grow, and then these allocations will happen. And we will again go back and update the bounds register. So the bounds value will be from 2 to 3. Yeah, it will become from 2 to 3. Any like disadvantages with this particular scheme? It seems like pretty good, right? In the sense, whatever we are using, we are just allocating page table entries only for the pages that we are using, and for the other pages we are not wasting any memory. But can you see any disadvantages in the scheme?
You keep track of more stuff.
Yeah, that is definitely one of the things. For example, we are keeping track of a lot of stuff, but let's assume the hardware provides us the support. That is definitely one of the things. We are like tracking a lot of things here, but more than that, let's say with respect to memory, okay, can you think of any scenario where this may use a lot more memory than needed? The page table entries, can you think of a scenario where the page table entries, where we may allocate space for invalid page table entries too? Just think about it, it's like really cool. Just one clue or one hint there is like to really think about how dynamic memory allocation really works. So when we use like dynamic memory allocation, we have something called the heap, and let's say like we have allocated a lot of memory, and suppose the user is freeing those memory regions. What if the first page in the heap and the last page, at that time it was the last page in the heap, if only these 2 pages are currently valid, and all the pages in the remaining pages in the middle, if they are freed, this particular scheme cannot handle that. Just think about this case, okay? Let's take the heap again, okay? Let's just talk about because this particular problem does not occur with code, because code is contiguous. And it also does not occur with stack, because stack is also, you can just like grow the stack or decrease the stack in the same way, okay? I mean, there cannot be like any space in the middle of a stack that is free suddenly. Or there cannot be any space in the middle of the code region that is free, okay? But this can easily happen with the heap. Just think about the heap. Currently, let's say like user initially allocated like the current page table for the heap is completely full or something, okay? It has all the 16 entries to be full. This is the page table for the heap, but suddenly all the pages that are here, okay? All the pages that are in the middle here, from here till here, the user has freed them up. Freed those memories, okay? Even though the user has freed all these memories, since this is allocated, and since this is also allocated, we are actually wasting this space in the middle, okay, for storing some page table entries, which will have the valid bit. The valid bit will be 1 and 1 here, and all these things will have valid bits of 0. Does it make sense? But this does not happen with the stack or with the heap. That's not a problem there. One more issue along with this is, does this issue make sense? Okay, so one more issue along with this is, in this memory, all the allocations usually will happen in the size of the page size. Okay, whenever you want to access the memory, usually we will just request a page size from the kernel, a memory of the size page size, and then use that particular thing. But even though everything happens in terms of page sizes, these page tables for the particular segments can be of arbitrary sizes. So for example, okay, let's assume this page table for heap in a real world system, this can have, let's assume 500 pages or something like that. If this particular thing for the heap just has 500 pages, then in the physical memory, this particular entire page table for the heap should be allocated contiguously. Does it make sense? Because this is again within this, it is again using the same, go to the base of this particular thing, and then go and access the contents that are inside that and stuff like that. And so a single page table here, okay, in this particular setup cannot be split into multiple parts. Is the problem clear? We cannot split it here because even though we are managing 3 different page tables for core, heap and stack, internally within each page table we are simply using a simple linear page table for a core, simple linear page table for a heap. You cannot split a linear page table at multiple places in the physical memory because the hardware will just assume if you are given an address in the heap, the hardware will just go to the beginning address, it knows the page table base register for the heap, just adds it with the size of the page table entry times the VPN, just goes in there, right? Since it does that, you cannot split up this page table at multiple places, and so that really becomes difficult. For example, if the page table for a particular segment grows very big, then it becomes difficult to find space for these page tables in the physical memory because you need contiguous memory for storing these page tables. This is the second problem with this particular scheme. So, what may be the solution? Yeah.
I have a question.
Okay, you have a question. Yeah.
Isn't the worst case scenario in this still equivalent to the just simple linear one?
It's still a megabyte.
So the worst case scenario in the scheme, is it still equal to the simple linear one?
Yeah.
With a megabyte of virtual pages in the worst case scenario, it still hasn't solved the space problem.
So yeah, we still haven't if the worst case here, in the worst case it's going to be all the worst case can happen here if all the code pages are full or allocated, all the pages in the stack are allocated.
Oh, I guess I just meant if you freed up 0 through 15 and the 16th one was there, that's still just as good as the other one. And anytime you're not in that scenario, it's better, right?
Exactly, yeah, it has the same problems with the other one, yeah. So this problem that we're discussing here is also present in the simple linear page table. Exactly, yeah. So the solution, okay, the solution for this, okay, answer the solution. So here the problem was the page tables were bigger in size than the actual pages. So the idea is, we started with base and bounds, then we went to segmentation and then paging, right? Now again apply the third idea, paging, for paging the page tables. So we are just going to page the page tables or split the page tables. In simpler words, we're just going to split the page tables into page size chunks. That's all we are going to do right now. Does it make sense? So I think, yeah. So the next idea is splitting this page table into page size chunks, and that is called multi-level page tables. We can take a break right now, and then we'll come and we'll just start discussing that. back by 7:55. Like an example address here, okay? For example, let's assume in this particular scheme, segmentation and paging, what do these three things mean, okay? So, just try those 10 bits here from our example. We have like 4 bits for the offset, then another 4 bits, and then we have the segment selectors here, the offset, right? Let's assume the address to be 20, the virtual address, let's assume it to be 20, so it is like 1, 2, 4, 16, I think this should be enough, right? So 16, and then 4 here, right? If this is the virtual address we are talking about in this scheme, then just from these 2 bits, we can figure out this is in the code segment, okay? But after figuring out that this is in the code segment, what we are going to do is like we are not trying to compute like a global VPN, like a VPN across the entire virtual address space, but we are trying to compute a relative VPN, okay, relative virtual page number. By relative virtual page number, what I mean is this particular thing that we have here, okay, will tell you the VPN VPN within the code segment. So this just means, okay, from this value of 1, we can be sure that this code segment has multiple VPNs, and the address that we are talking about is in the VPN 1 because it has a value of 1, right? This is the VPN 1, and within that particular VPN, okay, we will have within the particular virtual page, we will have like multiple bytes. We have 16 bytes because size of a virtual page is 16 bytes, and so you will go to that particular virtual page and then get this offset. This is the offset within that particular virtual page. So offset is just 4. So first thing is go to the code segment, then go to the virtual page within the code segment, and then go to the actual byte that you need, byte or address, okay, within the virtual page. Okay. Just think about this. If these 2 bits were 0, 1 in this case, okay? If these 2 bits were 0, 1 in this case, then we are talking about some address that is in the heap segment, but the VPN, if it is the same, 0001, okay? We are only considering the first, we are talking about heap starts here, then we are talking about this particular. From the global perspective, the VPN number is 17, okay, which would still be the case if you take the whole thing as a VPN. That's why I had it here, like the whole thing is the VPN, right? You may assume it to be like this is the global VPN number. I'm just making these terms up, okay? So like not real terms, just to make sure that you guys understand what is going on here. This is like the global VPN number kind of, which is like if you're having the VPN from 0 till 63, this is like the VPN number in the second example that we are talking about, where we have 0, 1, then 0, 0, 0, 1, then 0, 1, 0, 0. This is the address. Then this gives you the heap segment, and this just says you the first virtual page, okay? Again, by first here I mean we also have the 0th virtual page, okay? So I should, to be more clear, this is the virtual page 1, because we have virtual page 0 also in the code segment. This is the virtual page 1 in the heap, and within that we are trying to access the 4th byte because that is the offset. And so what I was trying to say is if you consider the whole thing as a VPN, this number would just be again 17, which will just map to the 17 number here. So the address that we are talking here is currently in this particular page. From the perspective of the heap, the first virtual page is at 16. So 0th virtual page is at 16, the first virtual page is at 17. Does this make sense? This is what is going on in this scheme, okay? So this becomes, if we name this to be a global VPN, then whatever we have here, you may have it as like a local VPN or within that segment, okay? Local VPN within that particular segment, okay? Okay, with this scheme, then we can now proceed to the next main idea. As we just saw, the problem was, there are two problems to address the problem of not having the page tables to be more than the size of the pages. All we are going to do is, again we are considering the same parameters just to make sure, okay, even in this case we are considering the virtual address space to be 1 KB, the page size to be 16 bytes, size of a page table entry to be 2 bytes, and we can also have like a physical address space, okay? The physical address size of the physical address is, let's assume it to be 4 KB. These are the assumptions that we are having. So in this case, if we have this, and if we have like some, let's say 0 to 1 KB of virtual address space, again this is the virtual address space that we are talking about. Now we know that we can like split this virtual. How many first point is how many virtual pages are in this virtual address. So that's what I will start with. Number of virtual pages is nothing but the total size, or like 1 KB divided by page size. It's going to be 16 bytes. So the number of virtual pages is nothing but 2 to the power of 10 by 2 to the power of 4 is 2 to the power of 6, or 64. Yeah, 64 virtual pages is what we have here. So we divide this into pages. In this address space, we'll have like a VPN 0, 1. We already saw this in the previous thing, because the previous thing also we had 1 KB, so this was 64. So now the next thing that we are going to see is, if we have 64 virtual pages, okay, we need 64 in a simple linear page table. We need 64 page table entries, right? Okay, we need 64 page table entries. But now, if we have 64 page table entries, okay, if we have 64 page table entries, what is going to be the size of these 64 page table entries? The size of the 64 page table entries is multiplied by 16, the page size, okay? Entire page table size is going to be 2 to the power of 6 times 2 to the power of 4 2 to the power of 10 bytes, or 1 KB. Okay, the entire page table, sorry, I think I messed this up.
Yeah.
These are like 64 page table entries, and we don't need like 16 bytes, but we just need like 2 bytes for storing a single page table entry based on our assumptions. So we need like 2 to the power of 6 times 2 to the power of 7 bytes, okay? We need 2 to the power of 7 bytes for storing the entire page table. But a single page has only 16 bytes, right? Page size is 16 bytes. So if we are going to split this page table, the high level idea is very simple. The high level idea is, if you have this thing as a simple linear page table, this was a simple page table, like a linear page table, okay? Now we are just going to try, you would have 0 till 63, right? Because you have 63 entries in this page table. Now you are just going to split this page table in the size of pages, okay? So this page table, you are going to split into multiple parts, and each part will be of a page size. And so a page size is 16 bytes, and one page table entry here, okay? One page table entry is 2 bytes. And so if it's very simple, 2 times 8 is 16. So you can store basically 0, 1 up till the 7th entry, first 8 entries, okay? You can store all these things in a single page. This whole thing, this whole thing gets saved in a single page. So I mean, then the first 8 page table entries in this page table can be stored in a single page. In a similar way, you can keep on doing this from 8 till 15, okay? All these entries, the next entries are going to be stored in another page, Okay, if we can do this in this way, okay, how many pages do we need to store this entire page table? Just think about how many pages do we need to store this page table. We have 64 page table entries, okay, and each in a single page we can have like 8 entries, okay, 8 page table entries. So you can have like 8, you need like 8 pages. You need 8 pages to store this entire page table, okay. If we need 8 pages to store this entire page table, then let's assume, okay, is it clear right now? I feel really bad to be teaching this at this moment, at this time of the class, where you guys may be like the most tired, but this would require the most concentration or something. So I'll try to I'll try to cover the high level ideas of multi-level page tables in today's class, and if possible, you can I can do that in the next class also. But let's see, how many of you are able to concentrate? Okay, this side. Maybe all of you should move this way, this side. No one from that. Okay, so let's see this, okay? We have now 8 pages for storing this page table. So the main idea is, since we have split them into 8 pages, they can actually be anywhere in the physical memory. Okay, if we have another mapping structure, okay, the idea is the high level idea here is since we have split them into 8 different parts, okay, of 8 pages, if we have one more structure on top of this, which stores the mapping information of where the first page table is stored, first part of this page table is stored, where is the second part of the page table stored, and that particular information, if we can have that, then we really don't need this whole page table to be stored contiguously in the physical memory. We can just split it anywhere that we want. Does it make sense? So that higher level structure that we are talking about, okay, is called a page directory. It's called a page directory. And since we have 8 page tables, right? So this 8 pages in turn just means each page has a single page table. In turn it means we have 8 page tables in this setup, right? In this address space we need 8 page tables for a single process. Again, still we are just talking about a single process, okay? Single process needs 8 page tables, but they are just parts of the same page table, basically, okay? 8 parts of the same page table. And so let's assume now we have those page tables here. These are the page tables. Page table 0, page table 1, it goes on till page table 7. But the important idea is this whole thing is just a page size, okay? This is just one page, and stored in a single page. Now we just have these 8 things, and each of these things are going to have in turn 0, 1, 2, up till 8 entries, right? And these entries are actually pointing to, by pointing here I mean they have the translations for the actual pages. So this may be pointing to, let's say, some page, some actual page, okay? This can be pointing to some actual page here. Okay? In this setup, now to store these page tables, okay, these page tables, we are going to create one more structure here with 8 entries, because we have 8 different page tables. We are going to have 8 entries here. Okay. Now we will start making some assumptions. Okay. The assumptions are the virtual pages 0, let's say, so since I already made 7 to pointing to a page, I will just assume 0, 1, 2, 3, 4, 5, 6, 7, all these 7 pages, then virtual page 8, then virtual page, let's say 8, 10, let's assume it to be 16, then 63. Only these are the valid virtual pages. Okay? Or maybe I'm not doing this, sorry. Seems to be a lot. So maybe just like virtual page is 0, 1, okay? Then virtual pages let's just assume virtual page is 0, 1, okay? 8, 9, 10, and 63. These are the only valid virtual pages. If these are the only valid virtual pages, okay, then what is going to happen? This page directory, this is called page directory. This page directory that we are having here is actually something that points to this particular thing, points to the first page table, and this, the last entry, this points to the last page table, and this points to the next page table. Okay? By pointing here, we just mean, let's assume that if this page is in the physical frame number, if the physical frame number for this particular page is, let's say, 701, okay? If the physical frame number for this particular page is 702, if this physical frame number is 708, okay? These need not be contiguous. Here I had like an example like 701, 702, but these can be just scattered anywhere basically. Okay, this number, this physical frame where this particular page table, part of this page table is stored, need not be the next physical frame. This can just be 601 also, okay? This can just be some number, that's the important thing here. So the actual page tables, part of the page tables are stored, scattered in the physical memory. Because it is possible to have them scattered in the physical memory, because we are going to store the information of where they are stored here. So here we will have 701, here we will have 601. Does it make sense? And here for the last one, we are going to have the frame number to be 708. This is how it's going to be. And since we say like only the virtual page is 0, which is here, then 1, which is here, then 8 is going to be here, 9 and 10 are also here, okay? So this is the code, you can assume this is the code, this is the heap, and this is the stack, okay? And the virtual page 63 will be here. Since only these are the virtual pages that are, since these are the only virtual pages that are actually valid in the setup, okay, what is going to happen is, this page directory at this time will only have entries like valid entries for these 3 entries. And all the other entries are going to have their valid bit, this is the valid bit, to be 0. Does it make sense? So this page directory, which has information about where a part of a page table is stored in the physical memory, okay, is the only linear structure that we need as of now, that needs to be stored contiguously. Does it make sense? So the only linear structure that we need as of now is just the page directory. And what is the size of this page directory? It depends, because usually the size, so this particular thing, the size of page directory entry, the entries that we have here, are called page directory entries. Very similar to page table entries, we call them as page directory entries. Size of a page directory entry, you can assume it to be the same size of a page table entry. In this case, usually they are the same size, okay? And so since we assumed a single page table entry is of 2 bytes, a page directory entry is also going to be of size 2 bytes in this case. So if this is true, then how much space do we need to store a page directory?
One page.
Exactly, we just need a single page because all it has is just 7 page directory entry, 8 page directory entries, and each page directory entry is of size 2 bytes, and so in total we need 16 bytes, and a page size is just 16 bytes. We just need a single page to store the entire page directory and so it is enough that this particular page directory will always be in the memory, should always be in the memory. So this page directory will always be in the main memory. I mean, because it is going to be accessed so frequently, it will always be there. And in our setup, even though this page table was so big, only 3 parts of the page table, whichever had valid pages in them, are actually whichever had valid pages are actually allocated in the physical memory. So the page tables here in between, okay, page tables 2 till page table 6, all these page tables are not even allocated. This is the coolest thing here. These are not allocated. We are not wasting any space for storing these page tables because those memory here, because these are the only valid virtual pages that we have in this particular process. You have a question?
How deep does that go?
That's a very good question. So how deep does that go? Because we are just considering a virtual address space of size 1 KB, right? We're just considering virtual address space of size 1 KB. But in reality, we saw that we have virtual address spaces of size 4 GB. So Linux currently uses a 3-level page table. Okay, Linux currently uses a 3-level page. This is like a 2-level page table. Whatever we have here is a multi-level page table, and it has 2 levels. The first level is the page directory level, and the second level is just the page table level. Okay, but in reality, we will have one more level which we will also discuss in this class. Okay, not in this class, yeah, it'll be in the next class, but yeah, this is the idea. And the reason. Okay, first, any questions in this about this? So maybe I can ask you a question. Can you think of a scenario, okay, in which the size, the memory space that we're going to use in a 2-level page table will be more than the memory that we'll be using in a linear page table? Maybe I'll just give 30 seconds for everyone to think, and then maybe just think can we use more memory in this 2-level page table in some scenarios when compared to a simple linear page table? Think.
If you have basically randomly allocated pages in your virtual address space, where you hit at least 1 in each of the page tables, you have now 9 pages maintaining your virtual address space.
Exactly, and so the answer was if we have let's say just 1 page that is valid in each of the page tables. If there is a situation where we have one valid page, at least one valid page in each of these page tables, then for that particular valid page, that page table needs to be allocated, right? And that is going to have more. So what is then, okay, that is the scenario, but what is, by how much more memory this is going to use? What is the size of memory?
16 bytes more.
Pardon?
Is that just 1 page more, like 16 bytes more?
For, yeah, it is 1 page for what? What, why is the difference of 1 page coming?
Because it has that 9. upper level page directory.
Exactly, this page directory, yeah. So in that particular scenario, the extra space that happens is mainly because of this page directory. Because in a simple linear page table, again you will have all these entries, but you will not have this additional page directory entry occupying a whole new page. So that would be the extra memory that may happen, but that is like an extreme case. Okay? It's like an extreme case because usually it is like the code segment, like some scenario like this will be the usual way like address spaces are allocated, and so usually that's not like really a problem. Okay? But theoretically, yeah, it can happen. So, shall we just like go through an example for this? Or not very sure if I can complete the example if I start right now. So maybe I'll postpone it to the next class, but I'll just like tell you like what maybe, so we were discussing about like higher levels of page tables, right? We'll just see like what may be the motivation for like a 3-level page table. So that does not require a lot of concentration. So here we were just considering a virtual address space of size 1 KB, a physical address size of 4 KB. These were our assumptions, okay? And what happens, is it possible to have a virtual address space of size 8 KB and the physical address space to be just 4 KB and the page size, okay, is still just 16 bytes. And again, all the other things remain, size of a page table entry and size of a page directory entry, we are just assuming it to be 2 bytes. First question is this possible? Is it possible to have a bigger virtual address space than the physical address space? Yes, I can see like people nodding. Yes, it is possible, because even though we have such a big virtual address space, we are not going to, a single process is not going to use the entire virtual address space. It is only going to use parts of it, okay? But the problem arises in the situations like this is nothing but 2 to the power of 13 bytes, okay? 2 to the power of 8 times 2 to the power of 10 is 2 to the power of 13 bytes. Now, if you have these 13 bits for this 13 bits, again you only have 4 bits, okay? You only have 4 bits for your offset, because you still have the same page size of page size of 16 bytes, okay? You just have 4 bits. And since you're going to fit each part of your page table in a single page, how many bits do you need for storing okay, I think I forgot to actually mention that in this setup, okay, a virtual, so let's again take, we are moving back to the old thing where we had a virtual address space of 1 KB with 10 bits, okay, with 10 bits. In this case, these 4 bits were for the offset, okay, and you needed like these 3 bits, okay, these 3 bits in this setup is called the page table index, PTI. These bits are called the page table index, and these 3 bits are called the page directory index. So what this just means is, if you have an address like 001, then 011, and let's assume it's 0010. Okay, in this case, just think about where does this address map to. Okay, this address corresponds to the page directory index of 1. Okay, page directory index of 1, which is nothing but here. Okay, page directory index 1 is here. Okay, and we know that it is pointing to some page table, and here using this page table index, we can easily find out what page table entry we are talking about. So here we say 3, right? This is just 3, 0, 1, 1 is 3. So we are talking about this 0, this is 0, 1, sorry, actually this is 3. I thought maybe I will have it as 2, so that we have a valid page, okay? This is 2. Now this is 0, 1 and 2. So we are talking about this particular page inside this page table, and this is the offset within that page. That's it. So now this particular thing is pointing to some page, okay, some actual physical page, and within that we are talking about the second byte within that page, 0, 1, 2. That is what this means. Sorry. So this just means which page table we are talking about, because there are a total of 8 page tables. Which page table we are talking about, and this page, so that is like an index in the page directory, okay? Shows you which page table we are talking about, or which page table does this address map into. And the second thing just means PTI, just means like within that page table, what is the index of the particular page table entry. And then the last offset just means now we got to the page, what is the offset of the byte that we are looking for. So one important change in this particular setup is like we don't have like a page table based register. The name of the register is going to be a page directory based register. So this page directory based register is going to contain the starting of this, because we really need to know where does this page directory exist in the memory, right? Because using the page directory, we can easily find out where are the different parts of the page tables scattered across in memory. So this is really needed. So the thing is called page directory based register. What I was trying to show you here is we needed 3 bits because we had like 8 entries or 8 page tables, okay? And here also we needed like 3 bits because a page directory entry needs 8 different entries to address each and every page table. Here in this case, when we just change this from 1 KB to 8 KB, we have this much. But again, within a single page table, a single page table is still going to point to only 8 different pages, right? A single page table is a single, like a part of a page table or page of a page table is just going to point to only 8 different pages, and so we still only need 3 bits for the page table index. But here we have like 6 more bits, right? So in this case, what happens is if you have the whole thing for the page directory index, then your page directory now has how many entries in it? 0 till 2 to the power of 6 minus 1, which is 63. So this whole thing, again, we go back to our previous problem where now the page directory is so big. The page directory is so big, which needs like 64 times 2, because each page directory entry is of size 2 bytes. We need again 128 contiguous bytes to store a page directory. Okay? To avoid this problem is where we introduce another level of indirection. Okay? Just page the page directory itself. Okay? And that is what is currently implemented. If you page the page directory itself, what we are meaning here is go and split this page directory into page size chunks. This is one page, this is like multiple pages, and then this is the last page of the page directory. Go and split the page directory into page sized chunks. If you do that, then you will like come up with a structure, something like again we are just discussing at a high level details. When you go and like do your worksheet, you really understand how messy it may get. Okay? So here it is going to be like one thing here. Okay. Now this is called, according to Ramsey, I think he calls it page directory 0, first level page directory, and then now this points to page directory level 1. Okay, I mean this is like the level 1, level 0, level 1. This is the level. This is the page directory level 1, okay, and within that you have a page. So this is like 0th directory basically, okay. The 0th page directory, the first page directory. In a way you will have like 7. These are page directories. This page directory, the global thing just points to all these page directories. And now these page directories, each of these page directories will be pointing to page tables. These are page tables. And each of these page tables are going to be pointing to the pages. This is the structure that we get when we go to a like 3-level page table. This is like level 1, level 2, level 3. You need to access 3 page tables or 3 structures to actually get to the page that you're looking for. Like, yeah, I think I will just complete with this. This is how a 3-level page table is organized in Linux. Exactly in Linux, this is how it is organized. So you can see like in Linux, these are the names that are actually used. This is called, the first level is called the page global directory. The second level of page directories in Linux, they are called like page middle directory. And then we have the page tables. And so Linux uses a 3-level page table. And this is how the 32-bit address space is split up. 0 till bit 11 is the offset. So 12, we have 12 bits for the offset, which means what do you infer from 12 bits for the offset? Exactly, we just have a page size of 4 kilobytes in Linux. 12 bits for the offset just means we have a page size of 4 kilobytes in Linux. Then we have these many bits for page table index, these many bits for, I don't really know how many bits, page middle directory index, the last 2 bits for page global directory index. And what is the maximum size that a single entry in the page global directory can point to? Maximum memory. Remember, we have like 4 GB of virtual address space, and you have only 2 bits for a page global directory index. So the maximum size that a single entry in a page global directory, maximum memory that it points to is actually 1 GB. Exactly, just 1 GB. So I'm just saying, this page global directory will just have 4 entries, and each of these entries will map to 1 GB of your virtual address space in total. There are like 2 things here, don't confuse it. Here I'm showing like a page directory entry with multiple levels, but in Linux it has only 4. At the topmost level it has only 4 entries in Linux. Okay? Okay guys, I think, yeah, we are done. How many of you felt like today's class was interesting? Okay, thank you. Okay. Let's meet next week, and if you have any other questions, please come talk with me, and I'll be here for the next 1 hour. I have like office hours. Thank you guys, and I'll see you next week. Yeah.